Let's see. There we go. Hello and welcome back to Calculus 1, section 2.2, Introduction to Limits. So let's see what the limits are. Yesterday we talked about the calculus in general. I mentioned that calculus consists of three parts: part on limits, part on derivatives, and part on integrals. Now, limits are going to give us base to understand both derivatives and integrals. And interestingly, that was the last concept that was defined. So both derivatives and integrals were defined before limits were defined, and limits are actually used to have some very rigorous definitions. So we'll do it in a correct order. So limits, what are limits? Well, the easiest way to understand what limits are is the fancy way to compute function value. So you are familiar that the function f of x, let's say x squared plus 2, right? X squared plus 2. X squared plus 2 has domain and range. Domain is the set of all input values that you can plug into x. And range is the set of all output values, in this case, all of the y's that you would get. Now, in pre-calculus, you would say f of 1 is 1 squared plus 2, and you have 3 as the answer. Now, in calculus, you are going to say limit as x approaches 1 of x squared plus 2 is also equal to 3. And probably the most natural question is why, right? If the thing in pre-calc worked just fine, why go and have a completely new thing written down in terms of notation and everything? Well, conceptually, these two things are very different. Sure, they gave us the same answer, but conceptually, they are very different. See, if I consider, well, this is going to be like, the red corner and the blue corner in a boxing match now. So if I consider the pre-calculus version of this, if I look at the graph, we know this is a parabola. It goes through, it's plus 2. So it's going through positive 2. It will look something like this. And then you go at x equals to 1, go up, and you see it produces answer of 3, creating the ordered pair 1, 3. So 1 intersects the line at this point. This point is 1, 3, and we are done. We have the same graph on the calculus side, but it's a different way of obtaining the answer. So what's happening on the calculus side is you are not computing at 1. You are going to, as you can see over here, approach 1. Remember how I said that calculus is a study of change, motion, right? This arrow captures that idea. X values will be going to 1. We don't care what's happening at 1. We care what's happening at all infinity of the points around 1. So observe what's happening here. I'm going to put these black lines as guidelines again, and use red and blue. See, actually, we can do this. As you are approaching 1, you will be walking on the line towards 1. Now, each point that it's getting closer, each x value that it's getting closer to 1, will produce y values that are climbing up the function which are the y values that are climbing this way. On the other side, you will have motion that goes against towards 1, which will go down the function, which will go down the y-axis, and yes, they meet at 3. I call this Romeo and Juliet approach. All right? Obviously, you have like blue for the boys and red for the girl. The most important stereotype, right, of growing up. So what you have here is motion captured through the progression of x values that give us different y values, and they converge at 3. So that's why the limit is still 3. Now, the interesting part is that I never computed at 1. 1 was inferred. We see that, the calculation at 1 is inferred. You see that the answer is 3 because the red and the blue arrow are going to collide at 3. Now, we can prove that if we use the chart of values. So what I'm going to do now is I'm going to put the point of interest in the middle of the chart. As here. So point of interest is 1. And I want to know what the answer for 1 is. These are going to be x values, these are going to be y values. So now I'm going to approach 1 with values. Well, let's come up with the red side first. 0.9 is smaller than 1. 0.99 is smaller than 1 but closer to 1. And 0.999 is also smaller than 1 and closer to 1 still. So I have these values, and you can see the red arrow progression this way, right? Now you will take abacus and compute these values, right, to see what they are. So 0.9 squared is 0.81 plus 2, so that's 2.81. The next value should be closer to 3 as you compute it, right? So let's compute those. We have 0.99 squared plus 2, and that gives us 2.98. You see that 2.98 is closer to 3. And then 0.999 squared plus 2 is 2.998. And that's even closer to 3. So you see that as x goes to 1, y goes to 3. So the red arrow goes to 3. Now let's check out the blue side. The blue side says, all right, so let me be 10 cents away, and then I am 1 cent away, and then 1/10 of a cent away. Hold on. These are supposed to be 1 point, not 0 point. There we go. Much better. So if you think of 1 as a dollar, you have $0.10, $1 dollar, and 1/10 of a cent. And now you compute the same thing, right? You will be calculating the values in the function. So 1.1 squared plus 2 is 3.21. 1.01 squared plus 2 gives us 3.02. Aha! The values are getting smaller, which is good, because we're aiming to get to 3, right? 1.001 squared plus 2 is 3.002. So now you also see that trend for the blue is going towards 3. So red approach and blue approach are both pointing towards number 3. So what is the limit? The limit is 3. And that's our answer here. The limit of function x squared plus 2 at 1 is 3. Now you will say, well, can I just plug the number in and compute? In some cases, yes. But it's very important to understand that, concept-wise, you are not doing that, actually. So sure, as a mechanic, it's going to work. You plug in 1, you get 3, and that's the answer. But as a concept, you are actually supposed to plug in infinitely many points leading up to 1. So not just these 3 values, but all infinity of them. You are supposed to plug in, and you are never, ever, ever supposed to plug in 1. The limit doesn't care what's happening at 1. It will give you that answer, what's happening at 1. But the limits do not compute at the value. They compute everywhere around the value and not at the value. Precalculus computes at the value and nowhere else. So now both sides of the story, right, are important and complement each other because certain situations are calculated with one, certain calculations are calculated with other, and some situations can be calculated with both. And we will understand those differences. But the most important part here is to understand, at least for now, what is happening with the differences between the two. And as I said, the mechanic of this, of plugging in 1 inside, is sure, it works when it works. It will not always work. So you'll have to be careful about that. So now we're getting to this, what they call preliminary definition of the limit. Because the real definition is actually in 2.7 at the end of the chapter, which makes 0 sense, but that's where it is. So preliminary definition for the limit will say that if f function is defined at all points near the x equals a, except possibly at a, which in our case is this 1, then the points will approach the y value of that calculation. So let's write the definition as is right now. So suppose the function f of x is defined for all x near a except possibly at a. We'll talk about this phrase. If f of x is arbitrarily close to L for all x sufficiently close to A, we write limit x goes to A of f of x is L. So this is the definition that technically says whenever x is approximately, well, let me draw a picture over here. So I'll put some arbitrary function f of x. Here is your x equals a. That will produce L Observe that the function doesn't have any jumps, breaks, anything like that. It works just fine. So technically what they say is that there is some neighborhood of points around A that will translate into the neighborhood of points around L, and then that's what I mean sufficiently close, right? If you take a look over here, won't you agree that these two numbers that we had, 2.998, and on the other side 3.002, are both screaming 3? Would you agree on that? That's what I mean by sufficiently close, right? If one number was 2.998 and the other one was 7.002, well, then yeah, clearly something is wrong, something is off, right? But since both of these numbers are really close to 3, then we can use, right, then we say that sufficiently close. So that's that part. And also, you might be confused with the statement except possibly at A. So suppose the function f of x is defined for all x near A. A is the value on x-axis, right? That was our 1 in the first example. So, and then it says except possibly at A. Now, what would that mean? Well, that's where the power of limits is. You see, if you have a function that is not defined at A, so this function is defined, this is function f of x, right? Passes vertical line test and definition, everything, so it's okay. Function is just fine. But the problem is that the function is not defined at value A. So function is not defined at value A, and if you try to compute this using pre-calculus, you would say that f of A does not exist because you can't compute, right? Remember the way functions are computed in pre-calculus. You plug in x, it bounces off of the function onto y, and you claim that y as your answer. That was the way the pre-calculus computed functions. So now, if there is a hole, there is nothing for the value to bounce off of, so it just shoots right through, and it never bounces off. So pre-calculus can't compute it. But the limit can. And that's the power of limits. So in calculus, the limit of f of x as x goes to A is equal to whatever the limit is. In this case, it will be some L over here. Why? Because limit never computes at the value. So no one cares that the value is not defined. We computed infinitely many points to the left, infinitely many points to the right, and they were all screaming this number. We never computed at A that wasn't there. So that's the power of the limit. Now, clearly, there will be some situations when limit wouldn't be able to do calculation, and the pre-calculus will. As I said, they complement each other. They're not competing. Well, the limit is a little bit stronger, but anyway. So that's the story of this phrase, suppose that the function is defined for all x near A except possibly at A. You have to have the infinity of points defined in the neighborhood. You do not have to have the point defined, because the limit will always work around that point, and the limit is fine in that case. So that's the idea of the limit. And now we get to consider certain cases. So first of all, you can always solve the limit problems by computing values, right? Which is the same idea with graphing. You can always graph a function if you compute x and y values as points and then connect the dots, like in a coloring book, right? So you don't have to know the basic shapes of functions, right? I gave you the basic shapes of functions in a previous lecture, right, yesterday. And I said, know these because you get to shift them left, right, up, and down, because there are no graphing calculators allowed on exams. But then every single one of these is actually, you can assign x's from -10 to +10, compute, you know, those 19 points, and connect the dots, right? And there you go. But obviously that's annoying and labor intensive, so maybe remembering these is a faster way to deal with things. The same thing goes with limits. You can just do the chart every time. You figure out, you know, 3, 4 numbers that are smaller than the number, 3 or 4 numbers that are bigger. You look at the trend, and you know the answer is there. So let's consider 4 cases here. So the first case, well, first 2 cases we already discussed, right? So here is my function f of x. I consider point A, which is returning limit L, and that is happening because, again, we approach from the left, which goes up the line, and then we approach from the right with blue, which goes down the function and down this one. And that's that. Then we consider the same thing, but now we have a hole in a graph, so the value at A is not defined. And as I said before, limits don't care, because, again, as you approach from the left, you will be computing at all values but not at A. And again, we don't care that it's not defined at A because we are never computing at A anyway. And we have pretty much the same thing that we have on the previous case. And you still have the limit L. Nice. Now, what I want to have over here is a function that is a piecewise function which has a jump like this. You see, in this case, your A is where the jump is, right? That's the interesting spot. The rest is well defined. Now look what happens. As you are approaching from the left, you are approaching on this part, and you are approaching this to be your limit. Let's call it L1. The blue side, approaching from the other side, is going to clearly be on the other line because it's to the right, and that one is going to return this value. Now you see that they don't agree, right? In this case, Romeo and Juliet do not meet. Do you actually know who they are? You do? At least like 3 of you? 4? 5? Smile over there is 6? All right. So yeah, that's that. And as you can see, they do not meet at the common location on Y. That case is the case where limit does not exist. That's the case where the limit does not exist because they do not meet at the common point. That the y values from these lines do not meet at a common point. And the third part, the fourth graph, is combination of variation of the second one. So we still have the same idea, but this time your value is dislocated. Okay, so you see the value is here. Now, this is the case where you have to be careful because both pre-calculus and calculus apply and they give you different answers. So you have to know which one is that you need. Look at this. If I am to calculate pre-calculus part, what happens with it? You shoot up until you hit the line. Well, you're going to pass through this open circle, but you're going to hit it here, and it's going to bounce here. This is your f of a. Right? It could be 7 or whatever it is. All right? So this point has coordinates a, f of a. It's defined. Remember how previously I said that the pre-calculus says does not exist because the line will shoot straight and never bounce off? Right? Well, now it hits the point and bounces off onto y and creates the y value. So the y value of this point is the y value of the function. Right? This is a piecewise function. The limit, if you go left and right and all of that stuff, will return this value here. So in this case, f of a and L are not the same, but they both exist. So I will go through all of these graphs again. Let me just fill in the red arrows and blue arrows and all of that stuff. So approach on the line, we go up, then blue, approach from the right, go down in this case, go down, and then they meet at L. Now, this is where you actually have to stop and study calculus, not just mechanically do problems. What are the differences between these four situations? Top left, limit exists, function value exists, and they are the same point. So f of a is equal to L. Top right, second graph, top right, the pre-calculus answer does not exist, but limit does. The third graph, the bottom left, function value exists. That's where the filled in dot is with the L2. That's what f of a is. So pre-calculus value exists. Limit does not exist because it produces two values. The red one produces the L1 and the blue one produces L2. So they don't meet at the common point, so the limit doesn't exist in this case. And then finally, the last graph, the bottom right, is the one where the point is dislocated. Right? So one point is moved out of the place. So the limit exists. The first thing I thought of when I was trying to understand this as a student was that, you know, a section of the bridge was missing. That was the first association for me for dislocated point. Right? You think of a bridge as a continuous right thing because people need to drive, but then one portion of it broke off and it's now in the water. Now observe what you can do. You can approach from this side, you can approach from that side, that you know that you have to fill this part in so that you can have the bridge work again, right? The portion of that bridge is, you know, maybe broken, maybe not, whatever, it's in the water, so we're just going to put the new one in, right? And fix the bridge and walk in, right? And then be able to drive over it or whatever. So that's this situation here where one point is dislocated, right? We are going to see these four graphs again in section 2.6 when we talk about continuity of functions. And the differences between these will be the driving factor for you to distinguish between continuous and discontinuous functions. Right now, we're just talking about the pure limit. Do they meet at the same point or not? Are the answers for pre-calc and calc, meaning computing functions and computing functions with limits, are they the same? So, in only one case, or out of these four, the calculation for the limit and calculation for the function value is the same thing, which is the top left picture. All of the other ones have something going on. Second one doesn't have pre-calculus answer because there is no value. The one below has the pre-calculus answer, but it's not the same as the limit, and the one on the bottom left doesn't have limit at all. So these are the situations that you have to consider as you go. So I hope you will spend some time looking at these graphs and understanding what's going on. So what we did so far is we understood that the limit is actually just the y value of the function. It's a different way to compute that y value than what you're used to, and that you can always cheat by using the chart of values. Always. You can cheat always with the chart of values, no matter what the problem is. Now, clearly, when expressions are a little bit big and annoying, you might want to know a faster way to do it, other than computing the values. Now, we have this notion of red arrows and blue arrows, and you saw me draw those on every single picture we had from the beginning, unless I talked about pre-calculus, obviously, only. So now it's time for us to talk about those arrows. So I have an arrow that is approach from the left. Now, if I have an arrow approach from the left, I actually have something that's called one-sided limit. And the one-sided limit notation is limit x approaches a, and you put this minus on a of f of x, and then you are going to get some value. I called it earlier L1, so you're going to get some number there. I also use the blue arrow, the Romeo arrow, which is approach from the right, which is limit x goes to a plus of f of x equals, and I'll call it L2 now. Right? That's the other one. And these guys are important because not every function has infinite domain. Think of a square root, right? It emerges at 0. So if you are calculating limit at 0, can you approach it from the left? No, because there's nothing there. Right? You can think of these approaches, guys, like walking on the line. You are walking on the function line. And if there is no function to walk on, you can't approach from that side. So let's consider the square root of x. If I draw the graph, told you already to memorize the look of square root of x. So this is our function f of x equals square root of x, right? So I can go and calculate the limit at any point I want, and I will have to use left and right and all of that kind of stuff. Except at one point, at 0. At 0, I can only write limit x approaches 0 plus for square root of x, and I'm going to get 0 as the answer. And the reason for that is, right, that's the blue approach. I can only do the blue approach for this particular one, because there is no function on to the left to approach from the left. So certain functions will only have, at some points, one-sided limit available. Now, as I said, at any other point you pick, you can do left and right approach, and they are going to meet at the point, and you're going to have the limit and all of that good stuff. Let me just write this in blue. So limit x approaches 0 plus of square root of x is equal to 0. That's the... Good. Now, all of this hints towards that first theorem that I told you about. The one theorem that will stay with you for as long as you have to compute limits. And that is the rest of the mathematical career. All right? Learn limits, guys. Half of your Calc 2 is limits. Half. Half is integration, and half is the limits, and then, you know, some sprinkles of derivatives here and there. That's what Calc 2 is. Like a pinch of derivatives. So, what is this big theorem? This big theorem builds on the left and right approach. And it simply says, if the left limit and right limit are the same, overall limit is that value. So that's what the theorem says. It's labeled in the book, you know, as theorem 2.2, but let's call it the two-sided approach. To compute limits. So, if limit x approaches a minus of f of x, so that's your left approach, is equal to the limit x approaches a plus of f of x, is equal to whatever value L, then limit f of x as x approaches a, which is from both sides, right, is that. So maybe let me just do the colors over here. So if, and then, there we go. So now what you have? You have your left limit in red, your right limit in blue, and your overall limit that we did since the beginning of the lecture in black. This is how you compute limits. You look at the left one, you look at the right one. If they give you the same value, that's that. That's the answer. That's the limit. And you move on with your life. So now, I talked earlier about the way to learn Calculus 1 and survive Calculus 1. That way is learning definitions and theorems. This theorem is the way to do problems. So let me, we had an example already, but I'm going to do another one. So here are 4 examples of using that theorem. Look, limit from the left and limit from the right are the same value, so overall limit is L. Limit from the left, limit from the right, the same value. Limit from the left, limit from the right, the same value. Limit from the left and limit from the right are not the same value. Therefore, limit does not exist. Aha. So there's your theorem 2.2 worked out on the 4 examples. they're arbitrary examples. That's another thing that you have to be very careful about in calculus. Concepts of calculus apply to functions, not to particular examples. Be very careful about that. Because if I do an example in class that it's a polynomial and then exponential, and then in the homework you hit the trigonometric function, there can't be any whining about that. Because the calculus concept applies to a function. And there is a book out there with 2,500 pages on mathematical functions where polynomials take a half of one page and exponential functions take a half of another page. Right? So what? 5,000 functions at that rate? There is no way, comma, in hell, comma, for me to do every single example of every single function that exists under the sun. So the argument that you haven't seen an example like this doesn't fly in calculus. It can fly in pre-calc, right, if we have a chapter on polynomials, right, and then the question is on exponential function. Well, clearly, you haven't had an example like that. But now observe that the theorems and definitions, they say f of x. So if I did the polynomial and I did exponential function and the homework is asking you for sine or a secant, well, right, you have to figure out how this works. That's why the most important part, the most important thing for the whole lecture is there. These are arbitrary lines. These are not polynomials. These are not trig or exponential. These are just squiggly lines that could be anything. And then you understand, okay, approach from the left, approach from the right. So, you know, we figure out that, and then whatever function you get, you can plow through it. But if you go and you try to memorize an example, okay, so he had x squared plus 2, so I can do x squared plus 5, I can do x, but if you see x cubed minus 3, you go, whoa, right? No, it's the same thing, right? You are learning the approach, and the theory, not the example or the problem. So with that being said, right, we already know that if these values are not the same, and I should write that as well. So if the values are not the same, then there is no limit. And we had that case. So let me give you another example of that. Let's think about function y equals 1 over x plus 3. Right, we talked about graphing these functions last time. We know that it's shifted 3 units to the left. So we are going to draw a vertical asymptote at -3. And we are going to draw our function, which is, 1 over x. We know what the default state of that function is. So now that we have this, what is the limit as x approaches -3? Well, you will look at the graph. The way to solve this is to actually do the red and blue approach, which is two-sided approach. So what do? I approach from the left. If I approach from the left, what happens to the y value? Where does it go? -infinity. Thank you. You see that? As you are getting closer and closer to 3, the y value is shooting to -infinity as fast as it can. What's happening with the blue approach? Right? Getting positive infinity. So, the answer is does not exist. Because left and right limit are not the same value. So there's another example of not having the limit. Now, most of your problems on the homework will be some kind of a piecewise function. You know, let's come up with something cute. F of x equals to, say we have what? Say we have, let's go with x for all x values bigger than 2, and let's have, you know, square root of x for all x values less than 2. Okay, let's graph this. We would like to check the limit as x approaches 2 of f of x. See, I can't even put one of the functions in here because it's going to approach two different functions at the same location. All right, so let's graph this just to see what it looks like. So clearly, we have something interesting happening at 2. So I'm just going to put this light line as a guideline to know that one function stays to the left of it and one function stays to the right of it. That's the idea of the piecewise functions. So y equals x is a 45-degree line, but it cannot exist to the left of 2. That means it emerges at 2 and continues at the 45-degree angle forever up. So we have 1, 2, 3, 4, 5, and so on. The square root will start at 0, 0, go through 1, 1, and end over here with the open circle, right? It ends at value square root of 2. And that value square root of 2 is about 1.4, so, you know, somewhere over there. By the way, the good quality OCD is very useful for these courses in mathematics. So now when you see it, right, if you are looking at the limit, the left limit, approaching from the left, is going to approach L1, which is square root of 2. And the right limit is going to approach 2. And those two are not the same. So, conclusion, because of the theorem, conclusion is that the limit does not exist. Because one-sided limit, one side, right, so the left-sided limit went to root 2, and the right-sided limit went to positive 2, and ta-da. So that's that. I hope you're not disappointed. That's the lecture on Introduction to Limits. So we'll restart for 2.3 after the short break.